Hi, and now we're going to talk about pressure again. I don't think we've filled out our notes in a while, so we're going to go to our notes first. I know that we've talked about our heat transfer, phase diagrams, heating curves, and all that jazz. And so we're going to start here with kinetic molecular theory. That's key concept 1.3. Even though we've talked about this before, I think it's just a good review. So what is pressure? So remember we talked about how pressure is the number and force of collisions. Remember I bang on the wall, and I'll bang on here too. Our official definition of pressure is the force per unit area. So the space that force is occupying. But for us, we really want to focus on those collisions, right? Those particles in a container as they hit the sides, right, and they bounce around, that they would increase the force. So pressure is measured in atmospheres, millimeters of mercury, torr or kilopascals. So we got to be able to convert between those, right? So our first question here says, how many kPa is in a tank that reads 950 torr? So again, we have a given, and our given goes first in our T-chart. Torr goes below, and I want kPa. These all equal each other, so the number in front of torr is 760, and the number in front of kPa is 101. So in my calculator, I'm going to type in 950. So 950. Right, so in my calculator, try to make it not so shiny. Here we go. 950, and then I'm going to multiply times 101 and divide that by 760. And I get 126.25. So this equals 126.25 kilopascals, right? This torr cancels, and I'm left with that unit that I want. Our second question says, how many atmospheres does a bubble deep in the ocean exert at 2,000 kPa? So I'm running out of space here, so I'm just going to make this my chart. Cheating, right? kPa will go on the bottom so that those cancel. And this time I want atmospheres. 1 atmosphere equals 101 kPa. Again, just look at the number in front of that unit. So 2,000 divided by 101 simply gives me 19.8 atmospheres. Okay. Now, using those conversions, we're going to flip to the back of our notes. Right? This also has temperature conversions, right? So we talked about this today, but for Kelvin, for a degree Celsius, you just add 273. So for every degree C, add 273, right? And that rhymes C and 3, right? Smiley face. So we can remember that. As we think about our gas properties, these are just the relationships that we made in doing our lab. So as volume increases, right, pressure is going to decrease, because they are inversely proportional. As the number of particles increases, when I add more particles, they're going to hit the sides more, so the pressure will then increase. They are directly proportional. As temperature increases, pressure will also increase because they're going to hit the side of the container more often and with more force. Put S's on those. And then as temperature increases, volume is also going to increase because that pressure increases, right? So those are related. Our combined gas law then, when we combine all these variables, was P1, the first pressure, times V1 divided by T1 equals P2 times V2 over T2. So using this formula is going to be important for us, and we're going to do 3 examples, okay? Our first one says a ball is filled with air and it has a volume of 50 milliliters. So I like to, as I read, write my numbers down. So volume of 50 milliliters means that is volume right here on the side. At a pressure of 1 atmosphere. So my first pressure is 1 atmosphere. The ball is pushed underwater to a depth of 30 feet. Well, I don't have depth up here, so I'm going to leave that alone. Where the pressure is now 2 atmospheres. All right, so I've doubled the pressure, assuming that temperatures remain the same. So if these remain the same up here, they're the same on both sides, we can either ignore it or you can make up a number for both if you'd like to. But I'm just going to make them both. We don't need these, right? So when we see the word same, we don't need those, right? What volume does the gas occupy at this depth? So for here, because there's no temperatures, then I don't need this part of my formula. So I'm only simply going to relate my pressure and volume. That's like the first lab that we did, 1.9a. And so I'm only going to use that formula, P1 times V1 equals P2 times V2. My P1 I wrote down as 1. My V1 was 50. My P2 is 2. And I don't know V2. That's what I'm looking for, right? So to get V2 by itself, I'm going to divide by 2 on both sides. 50 times 1 is 50, and then 50 divided by 2, that is 25 milliliters, will be V2. Now let's do a little more complicated one, right? So our second question here says, the gas in an oxygen tank is at a pressure of 3 atmospheres at 25 degrees Celsius. So again, let's write our numbers down as we see them. A pressure of 3 atmospheres means this is 3 atmospheres. At 25 degrees C, that's a temperature, 25 degrees C. And for every degree C, add 273 before you even do anything else. So 25 plus 273, that's 298 Kelvin. What would the gas pressure in the can be at 52 degrees? So what would the pressure be? So that's what I don't know. If the can went up to 52 degrees C. Again, add 273. 52 plus 273 is 325 Kelvin. This doesn't talk about volume. So if we're in a tank isn't really going to change its volume like a balloon would or something that's stretchy. And so again, if we don't have volume, I go back to my formula up here at the top. That means I don't need either of these volumes as well. So my formula becomes P1 divided by T1 equals P2 divided by T2. So I'm simply going to write that down. P1 over T1 equals P2 over T2. I'm going to plug in my numbers here. 3 divided by 298 equals, I don't know the new pressure, but I know the temperature went up to 325. Because my variable is being divided by 325, I'm going to multiply by 325 on both sides. So in my handy dandy calculator, I'm going to take 3.00. I'm going to divide that by 298. 3.00 divided by 298. And then I'm simply going to multiply that by 325. That gives me 3.27. So P2 equals 3.27 atmospheres. If that pressure is too much for that can to hold, it'll explode and break your windshield, just like that lady in our video. Our last one that we're going to do says a helium-filled balloon has a volume of 50 liters. Okay, so there's my volume. At 25 degrees Celsius, for every degree C, add 273. Since it's the same as the first question, I'm going to write that down again. And 1.08 atmospheres. They must be in Death Valley because they are below sea level. With their balloons. Maybe they're celebrating something. What volume will it have? So I don't know the volume. At 0.855 atmospheres and 10 degrees Celsius. So remember, for every degree C, add 273. That's 283 Kelvin. So really, this is what happens when you take a helium balloon, apparently in Death Valley, and then you let it go, right? That helium balloon floats into the air because helium is less dense than the air around it. There's the bell. And so if we let that go into the atmosphere, the pressure goes down until you get all the way to zero, because space has no pressure, it's a vacuum. And then the temperature is also going to decrease. It gets really cold in the atmosphere, right? And so we're also going to have a low temperature up there. What's going to happen to the volume of that helium balloon? So we're going to find out. Here we don't get to ignore any variables, right? We've got one of everything except for volume, which is what we're solving for. So P1 times V1 over T1 equals P2 times V2 over T2. My P1 is 1.08. My V1 is 50. My T1 is 298 Kelvin. What's going to happen when I decrease that pressure to 0.855? I don't know volume, but I know that the temperature is 283. So this is a situation where I'm going to cross multiply to solve for my V2. So I'm going to cross down first. Okay. I'm going to take my 1.08, multiply it times 50, and when I cross multiply, I'm also going to multiply by the denominator 283. That gives me 15,282. That's going to equal, well, I'm going to cross multiply this side. So 298 times 0.855 times V2 gives me 254.79 times V2. Now to get V2 by itself, I'm going to divide by 254.79 on both sides. (15,282) divided by 254.79. That's going to give me 59.97. And that's going to be in liters for V2. Okay, now you try.